Hello and welcome to ASIC seminar series. This is John, the seminar coordinator, and together with me is Miss Kathy Medney, and she is our communication specialist. Kathy and I will be today's moderator, and we are excited to have our speaker, Professor Joe Johnson, joining us from Ohio State. A few things before we start up. The seminar is being recorded and will be later published on our YouTube channel. Please be free to ask questions. You can ask verbal questions by raising your virtual hand, and we will unmute you. You can also send us a text message in the chat. And let me briefly introduce the speaker before we get started. So Professor Joe Johnson is a burn and sealing endowed professor in the Department of Electrical and Computer Engineering and Electron Science Laboratory of the Ohio State University. His research interests are in the areas of microwave remote sensing, radio wave propagation, and electromagnetic wave theory. He has served on the science team for NASA's SMAP and Cygnus missions, and as the principal investigator of the CubeSat radiometer radio frequency interference technology validation mission, the CUBE RRT. Professor Johnson also serves as principal investigator for the ultra-wideband software-defined microwave radiometer mission for measuring the 0.5 to 2 gigahertz brightness temperature of Earth's cryosphere. Let's welcome the speaker, and I will turn this over to Professor Johnson. Professor Johnson, please proceed.
Okay. All right. Thank you for that introduction, John. And thanks to everyone for attending this seminar, for the opportunity to talk about our work in microwave radiometry at frequencies less than 1.4 gigahertz, which we think is an interesting emerging technology for performing Earth remote sensing. As I get started here, I'd like to acknowledge many collaborators who have supported the development of this technology. And you can see a partial list of them here, including many collaborators at Ohio State, at CNR, the Institute of Applied Physics in Florence, Italy, the University of Michigan, at Monash University of Australia, at NASA, Goddard, both Goddard and JPL, and at other organizations, as well as I want to acknowledge the support of NASA's Instrument Incubator Program, of the Cryospheric Science Program, the NSF Office of Polar Programs, the Program of National Research in the Antarctic of Italy, and the Alfred Wegener Institute, who have led the Mosaic campaign. Okay, so the motivation for this idea of using microwave radiometry at frequency less than 1.4 gigahertz stems, it starts from the realization that over the last decade or so, 3 spaceborne microwave radiometers operating at 1.4 gigahertz have demonstrated a lot of valuable remote sensing products. And you can see those 3 missions down here in the bottom, which are SMOS of the European Space Agency, the Aquarius mission of NASA, and the SMAP mission of NASA, all 3 of which use measured thermal emission from Earth's surface between 1400 and 1427 megahertz, and in doing so could measure properties of Earth like the soil moisture and the ground surface, the salinity of the seawater. We're seeing new products now in terms of vegetation optical depth. They also have demonstrated the measurement of the sea ice thickness for thin sea ice, as well as some information about temperatures inside of ice sheets and the properties of the upper furrent of ice sheets. All those are very valuable products that this band is pretty much sometimes the only way to sense this kind of information. Now we're talking about, microwave thermal noise being emitted from Earth's environment at these low frequencies, okay, 1.4 gigahertz, where the wavelength's about 23 centimeters or so. Okay, so it's a long wavelength. And as you know, if you want to for a radiometer, the resolution you get on the Earth's surface depends on the size of your antenna relative to the wavelength. So at these low frequencies, you need a very large antenna or a large antenna aperture to get to improve your spatial resolution on Earth's surface. And so because of that trade-off between antenna size on a satellite and spatial resolution on the ground, we're typically talking about spatial resolutions on the ground ranging from about 40 even up to 100 kilometers for these kind of instruments. Okay, so this is not reading the postage stamp from space. This is trying to measure large-scale phenomena that still are, very useful for understanding properties of Earth system and Earth environment. And these measurements of these systems have had a significant impact on our ability to model Earth's environment. Okay, so one motivating factor for this work is the success that's been demonstrated using 1.4 gigahertz. Another motivating fact for this idea is that at the same time, there had been a lot of innovations over the past, say, 20 years about improving the ability of microwave radiometers to coexist with communication systems operating in the same band. From the microwave radiometer point of view, a communication system in the same band is producing RFI, or radio frequency interference. Okay, but technology developments have shown that it's possible to include processors within our radiometers that can do some filtering of the interference in many cases, and then still be able to measure the natural signals coming from the Earth environment, even if there are other communication systems operating there. Doing that causes some degradation in your measurements, so it's not perfect, but there is at least some potential to make measurements when we have communications users operating in the same band. Now the SMAP, those three missions I talked about, SMAP, Aquarius, and SMOS, all only operated within this particular part of the spectrum, 1400 to 1427 megahertz, that's protected, so that no one's supposed to be transmitting in that part of the spectrum. That said, there's still some transmissions there, and the SMAP mission in particular included a processor on board the spacecraft that improved the ability in ground processing to do filtering out of RFI contributions. And recently, another mission, the Cubert mission, for which I served as the PI, which was supported by the NASA INVEST program, took this a step further and demonstrated having a processor on board the spacecraft that could try and filter the interference in real time in a much larger bandwidth. And here's a picture of the Cubert CubeSat. It demonstrated a processor on board that could take a 1 gigahertz wide channel and do RFI processing in real time. And so the advancement of those kind of technologies shows that it's more and more feasible to try and see if we can coexist with other communications users, even in non-protected parts of the spectrum. And I should point out that similar systems to these are being developed for the EU's SIMR mission and for the MEDOP mission. So these technologies are advancing into being deployed in space. So those two things coming together enable us to think about, well, since I have these technologies and I know 1.4 gigahertz is valuable, would it also be valuable to extend that lower frequency range down to even lower frequencies, say 500 megahertz? So since 2013, our team at OSU has been investigating that, trying to measure Earth's natural thermal emissions in this frequency range and see what kind of scientific products we could get out of that. And one reason you might think you get some advantage is because lower frequencies can penetrate more into geophysical media. So if we have materials where we'd like to penetrate into something, using these lower frequencies might help us get more information about deeper inside of something. Now again, in this part of the frequency spectrum, we have no protected spectrum at all. There's transmitters throughout this entire range. So it's definitely a technology where you're going to have to coexist with other uses of the spectrum. And so we can say that we have to design the system to try thermal noise measurements in the presence of RFI. And that means we've got to be kind of opportunistic in our approach. We can't guarantee that we'll have access to the spectrum 100% of the time, but if we can just have access some fraction of the time, that may be good enough for us to get science information out of these bands. And if you think about that, your success may be more likely in less populated regions, like at higher latitudes, for example. Another interesting thing about this idea is that if we measure over these wide frequency bands, not just at a narrow band, but over a wide frequency band, we might be able to chop the spectrum up into pieces and measure the Earth's brightness temperature, which is what we call the thermal noise power emitted in this range. We scale it in terms of brightness temperature. We can measure the brightness temperature versus frequency and thereby get additional information from this sort of hyperspectral measurement of brightness temperature versus frequency. And so we'll be looking at that as we go through this talk. So in this talk, we want to talk about recent progress in this area, along with an overview of challenges, opportunities, and recommendations for next steps here. And I should comment that portions of this talk were generated with that set of co-authors that I listed and presented at the MicroRad 2020 conference, and are also included in a journal article that we have in the publication process. So let's start off taking a look at some of the science products that might motivate this kind of measurement. One of those science products is trying to measure the physical temperature inside of thick ice sheets like those in Greenland and Antarctica. Okay, so the temperature inside the ice sheet is an important parameter because it governs how stiff the ice is, and that influences its dynamics. And if we want to forecast the future of the ice sheets, we need to be able to model those dynamics very well. At present, the temperature inside of an ice sheet is only measured at places where you bore holes down to the bottom and can stick probes in there to measure the temperature, which of course you can only do at very sparse locations, and therefore you don't have remotely sensed information about temperatures deep inside of ice sheets. And so if this measuring thermal emissions over a wider band could help us get that kind of information, that could be a very valuable thing. And this slide is kind of giving an overview of some of the things I'm going to talk about in the next few slides here. So why don't I just go on to the next slide here. So one idea here is that, here we've got our thick ice sheet. Okay, so we got air up here, ice, and then bedrock at the bottom. This ice sheet might be kilometers thick, and we'd like to determine the temperature as a function of depth inside the ice sheet, okay, by measuring the thermal noise being emitted from this ice sheet. So our idea here is that this is where we can use this multi-frequency kind of idea. If we can measure at lower frequencies, say 500 megahertz, then those thermal emissions are going to be coming from a greater depth into the ice sheet. At 500 megahertz, we can sort of see through the ice sheet to greater depths, and so lower frequencies are going to be more sensitive to emissions from the lower parts of the ice sheet. On the other hand, higher frequencies are going to experience more attenuation, so they might be sensitive only to the upper parts of the ice sheet. So by measuring the thermal noise as a function of frequency between 500 and 2000 megahertz, say, I could try to infer information about temperature as a function of depth. And in particular, this illustration here, it tends to be the case that ice sheets are warmer lower into the ice sheet than at the top, because the ice kind of acts as an insulator above the upper ice acts as an insulator of the lower ice. And so if we had warmer ice at the base, then our brightness temperature might be a decreasing function of frequency if we plotted brightness temperature versus frequency. Because again, the lower frequencies are seeing the warmer ice towards the bottom of the ice sheet, whereas the higher frequencies are seeing the colder ice towards the top. And again, by making this measurement of brightness temperature versus frequency and combining that with a model of how we think the emission process works, we can try to back out what we think the temperature profile is inside the ice sheet. So that's one of our geophysical products that we're interested in. A little bit more detail here, the physics of the measurement, how does that work? So this equation is telling us the brightness temperature we would measure with our radiometer as a function of frequency, F here, can be written as the expression on this right-hand side, okay? Now that expression involves sort of a transmission out of the upper part of the ice sheet. Whatever comes from below has to sort of transmit its way through this upper firn layer on top of the ice sheet. That's what this term represents, which is a function of frequency and the density profile of that upper part of the ice sheet. But then the thing that's transmitting through that cap is basically a weighted integral over the height of the ice sheet of the temperature profile, the thing we'd like to infer here. The temperature profile is a function of depth weighted by the RF attenuation, the local RF attenuation at a given depth, which is this alpha coefficient here, the attenuation rate of the ice. And then that emission from a particular depth in the ice has to propagate its way through all the ice that's on top of it, and therefore gets attenuated as it propagates through that overlying ice. That's what this term is here. And then if there's any emissions from the base that make it out of the ice sheet, those would be attenuated through the entire ice sheet thickness. Okay, so that's what this expression is showing us here. And if we focus just on this, this term right here, we can see that we could rewrite that term as this emission contribution, this brightness temperature contribution, is just an integral over the temperature profile, again, the thing we're trying to infer here, times some weighting function, just like when we do atmospheric sensing of temperature with radiometry. And that weighting function is basically this, attenuation rate times the total attenuation overlying a given layer, this factor here. And so if we look at that weighting function, in particular look at it as a function of frequency, we can learn something about how sensitive is our brightness temperature to the temperature profile at different depths. Okay, this weighting function is a function of depth and frequency. Okay, so this next chart is looking at some of those weighting functions. Okay, so here we have some representative temperature profiles inside of an ice sheet. The blue case being at the Dome Sea location in Antarctica, which goes up to about 3 kilometers thick ice. The red location being a shallower location, the Di3 location in Greenland. Different temperature profiles at these two locations. We can take these temperature profiles and compute what those weighting functions would look like. Okay, so this is a plot of the weighting function versus depth for different frequencies shown here, okay, in this curve. And we can see, as we might hope here, that the weighting functions of different frequencies peak at different locations. For example, 500 megahertz peaks at greatest depth, whereas 2000 megahertz is more emphasizing shallow depths like we talked about earlier. So this does kind of confirm our intuition that lower frequencies might be giving us more information about greater depths, higher frequencies about shallower depths. And we can see here also illustrated as this the values of the function illustrated in a color plot versus frequency and depth. And again, showing that at lower frequencies we're more sensitive to lower depths, higher frequencies are more sensitive to shallower depths. So by combining brightness temperatures over multiple frequencies, we can try to infer the temperature versus depth. Now I should point out that these weighting functions themselves are dependent on the temperature profile. So it's not entirely a decoupled problem. And with a different temperature profile, as in Greenland, we get a different set of weighting functions. And so we need to do a model-based type retrieval to back out this information. But even in this case, we can see that the different frequencies are sensitive to emissions at different depths, again, sort of confirming our intuition. Okay, so that's sort of our motivation for thinking about trying to sense temperatures inside of ice sheets. And we think if we can accomplish this by making multi-frequency radiometric measurements, that could have a big impact on this science topic. Okay, moving on to our next potential geophysical product. This is related to the thickness of sea ice. Okay, well, everybody knows the sea ice cover is changing a lot in recent years, and there's a lot of interest in trying to monitor it, understand how it's changing, forecasting the future of the Arctic, and so on. So if we could sense the thickness of sea ice, that could also be pretty impactful. Now, to do that, we have to understand the thermal emission from sea ice as a function of the sea ice thickness. Okay, so here we have a kind of a nominal plot, one example plot illustrating that. Here we're plotting the brightness temperature of sea ice as a function of its thickness for different observation frequencies, okay, ranging from 500 megahertz, the blue curve here, to 1.4 gigahertz, the green one, the standard SMOS, SMAP kind of observations, to 2 gigahertz, the red one. Okay, and this is for a nominal sea ice salinity of 6 part per thousand and temperature negative 10 Celsius. What we see from looking at these curves is that our existing SMOS, SMAP kind of instruments, they're very sensitive to ice thickness in sort of the shallow ice region, up to about 50 centimeters, as you can tell by the rapid change in brightness temperature that occurs there. But once we get past about 50 or 60 centimeters or so, things saturate, and we're no longer very sensitive to ice thickness past that point. So our existing sensors can do a pretty good job for thin sea ice. But if we wanted to try and continue to be able to sense thickness to greater thicknesses, we can see that we need to go to lower frequencies here. For example, at 500 megahertz, we're still increasing in brightness temperature even to sea ice thicknesses greater than 125 centimeters or even more. So we think that by expanding the frequency range to include these lower frequencies, we can do a better job of sensing sea ice thickness, even up to sort of the 1 to 2 meter thickness range that we can't currently sense with our existing L-band radiometers. And we've actually developed an instrument. We've flown some campaigns. I'll talk a little bit more about our UWB-RAD instrument later. This is an example flight path we had over sea ice north of Greenland. And we've done some retrievals like this to show that we can retrieve sea ice thickness to greater depths than we could use just using 1.4 gigahertz alone. So that's another product of interest. A third product of interest is the salinity of the sea surface. Okay, so as I mentioned before, SMAP, SMOS, Aquarius, they all can measure the salinity of seawater, which is an impactful thing to measure. There's really no other way to do this on a large scale. It's impactful because it tells us about ocean circulation patterns that are very important for understanding our Earth system and so on. So those have been great measurements. They've really accomplished a lot from SMAP, SMOS, Aquarius. However, it turns out the existing systems do very well, except in cold waters. Once the water starts to get cold, as it does at high latitudes, then the sensitivity of the 1.4 gigahertz brightness temperature to salinity degrades. Okay, and that's kind of indicated in this plot here. We're looking at the change in brightness temperature with salinity, okay, in parts per thousand here, at different frequencies yet again. Okay, so this curve down here is 500 megahertz. Our existing measurements are at 1.4 gigahertz, and we can see definitely that the sensitivity gets reduced as we go into cold waters here, 0°C waters. But by going to lower frequencies, we can get that sensitivity back to try and improve our precision in cold waters. And these plots over here are from some mission studies that have kind of shown, with just a 1.4 gigahertz system, your precision in measuring salinity degrades in colder waters. But if we were to add some lower frequency channels here, for example, at 800 megahertz, we could get that precision back. So again, this kind of improvement motivates trying to do brightness temperature measurements at frequencies below 1.4 gigahertz. Okay, yet another science product we're interested in is trying to extend our measurements of soil moisture or permafrost properties. Again, SMAPs and SMOS have been very successful demonstrating soil moisture measurements in the upper 5 centimeters of Earth's land surface. It's really been impactful. But again, if we could extend our frequency range to lower frequencies, we might be able to sense soil moisture information to even greater depths, or else extend the range of vegetation through which we can continue to sense soil moisture. And this is a little example of that, comparing the penetration depths as a function of frequency in soil of different soil moisture contents, ranging from drier to wetter soils here in the three curves. And we can see as we, again, that as we go to lower frequencies, our penetration depths increase beyond what they are at 1.4 gigahertz, so that we could potentially extend our ability to sense soil moisture to greater depths. And our co-author, Jeff Walker in Australia, has been doing some airborne measurements at these frequencies. Sometimes we call frequencies in this range P-band. So he's been flying a radiometer operating at both L and P bands and looking at the brightness temperatures that exist as a function of the soil moisture and other land surface properties to try and understand how P band might help us extend our ability to measure soil moisture over the Earth's land surface. So this is another motivating geophysical product here. Permafrost is also of interest because it might extend our ability to sense the active layer depth in permafrost, which is a pretty impactful thing for understanding Earth system changes as well. Okay, so those are some of the motivating science properties. There are others as well. These are kind of the ones we've been focused on at OSU. And as I mentioned, over the last several years, under the support of NASA's Instrument Incubator Program originally, we've built an instrument we call the Ultra Wideband Software Defined Microwave Radiometer, or UWB-RAD, that we've been flying in airborne campaigns to try and gather evidence that we can do the kind of remote sensing I was just talking about. Okay, and again, we got to always keep in mind, these are heavily used parts of the spectrum. So any kind of instrument we're going to use here needs to be able to detect and filter RFI contributions. So for UWB-RAD, we did that by taking this part of the spectrum, chopping it up into 12 frequency subchannels. And then in each of those subchannels, we further subdivide those into 512 individual subchannels. So all told, we've got 6,144 frequency channels that we measure instantaneously with this instrument. And that helps us with filtering out RFI. If there's some interference, it's localized in frequency, we can try to figure that out and throw out those subbands of frequency and try to keep those that we don't think contain RFI. We also do some time domain filtering. We try to filter interference both in the time and frequency domains and try to retain only the thermal noise containing parts of the spectrum. Now, when we do that, we throw out parts of the spectrum that we might have had otherwise, so we degrade the sensitivity of our measurement. But we found that since we're measuring over such a wide bandwidth, we can still get sufficient spectrum in many cases, at least in UWB-RAD measurements, to still make science measurements that support producing science products. So we just have a single antenna looking straight down. Keep things simple. We look straight down at one polarization, circular polarization, and you can see some of the other properties of the instrument here. I'm happy to talk about those in more detail. We published multiple papers you can find to give you more details on this instrument. Here's a plot of our frequency subchannels. Again, we have 12 channels here. This is the frequency ranges they cover between 500 megahertz and 2 gigahertz or so. And we did have to put a gap in here because of some of the interference on board the aircraft. The bands marked with the stars. We've also built smaller versions of the instrument that only have 4 channels, and those are the 4 channels that are included when we had smaller versions, for example, as deployed in the Mosaic Sea Ice Observing Campaign. Okay, so we've taken this instrument and we've flown it now in 3 airborne campaigns. 2 of those were in Greenland and 1 was in Antarctica. The Greenland flight paths are shown here. Okay, one of the campaigns only produced this blue line. It was our first test of the instrument and so on. The other campaign, we overflew that blue line once again and then got these extra red lines. The flight paths were designed to observe locations where we had boreholes so that we knew what the temperature profile inside of the ice sheet was. And also we have this flight path that went up here over Arctic sea ice, as I mentioned earlier. We also got some other regions. We also measured in the transit to and from the aircraft base here. So we have other data sets as well. But we've been looking at these data sets and with a focus here, first seeing that we can measure anything at all in these bands. They're not totally unusable. And then second, trying to see if we can measure things like ice sheet temperatures or sea ice thickness. Here's an example showing the spectrum occupancy we had to contend with. Again, we have this is a spectrogram. Okay, so this is showing our 12 frequency channels here between 500 and 2000 megahertz as a function of time. So this is about half an hour's worth of data here. Okay, near a takeoff from the Thule Air Force Base in Greenland where we were based. And this is calibrated brightness temperatures over here shown in kelvins. Okay, the color scale is brightness temperature. And you can see we're near this Air Force base. We're on board an aircraft with many transmitters and so on. So this doesn't look very much like thermal noise when we take our first look here, because thermal noise should be smooth, relatively smooth in frequency. It may vary slowly. It should be relatively smooth in time. We can see a lot of things bumping up and down here rapidly, which is definitely not a thermal noise type characteristic. So this is the raw data before we try to do any interference processing. After we apply the interference processing, which again involves throwing out time subsamples, throwing out frequency subsamples that look corrupted, we can seemingly get rid of a lot of that interference to create something that looks more like thermal noise type information. Okay, so if I compare those two, you can see by using pulse type interference detection, by using cross frequency detection and kurtosis detection and so on, as was demonstrated in the SMAP mission of NASA, we can do what seems like a pretty good job of filtering out the interference so that we can create what seem to be scientifically useful brightness temperature measurements of thermal noise in these frequency bands. Okay, now you can see we do lose some parts of the spectrum in doing that. But again, we're kind of oversampling here and the aircraft flies slowly. We have a lot of integration time and so on, so that we still can produce reasonable sensitivities for our brightness temperatures here, even though we do lose the sensitivity that we might have achieved if we had access to the entire spectrum. Okay, so after doing that, we can then take these 12 bands that we filtered, go back and integrate in time and frequency to produce brightness temperatures here plotted versus longitude as we fly over the flight path for our different 12 frequency channels. Okay, from 530 megahertz centered frequency to 1980 center frequency. And in particular, this part of the flight path was going from the sea surface over here, which is off the scale, water's cold at these bands, to flying up over the rocky coasts of Greenland, going over some different features, coming over to the percolation region of the ice sheet where there's a lot of melt and refreeze that seems to give rise to scattering features in the ice that cause a scattering loss in the brightness temperatures, to where over here we get out over the colder parts of the ice sheet where things are more smoothly varying. And now that we've got these 12 frequency channels, we can look at the emission spectra coming from different regions and again try to infer information such as ice sheet temperatures or other information from those measurements. Now we do see still some evidence of RFI remaining here. We continue to post-process these. We do a lot of RFI processing on these data to try and mitigate these effects, and many of these are still can still be detected using additional post-processing. Okay, so one of the science projects we wanted to demonstrate was temperature profiles inside the ice. So as I mentioned, we want to do this by combining a model, some sort of model information about what do we think these temperatures are like inside the ice sheet, some sort of a priori information on that, with the measurements. Where putting those two together, you can correct anything that was off in the model to try and get it to match reality. So the model we used here is one that's pretty simple for the temperature profile inside of an ice sheet that was applicable here because we were only flying over these very dry and more static parts of the ice sheet. there's a model called the Robin model. It's kind of a zeroth order temperature profile model that says that the temperature profile inside of an ice sheet should be related to its surface temperature, the geothermal heat flux at the base of the ice sheet, and things like the ice thickness and the accumulation rate. So we have this model to kind of give us some guidance on what those temperature profiles might be like. And in this particular retrieval, we retrieved these 5 parameters. Since these are the parameters that govern the temperature profile, instead of retrieving the profile as a function of depth, we just decided to retrieve the parameters of the model here. And again, by running the model, trying to tune it to match the measurements, the model prediction that comes closest to the measurements is what we determine as relating to the retrieved temperature profile. Now, one thing I should point out, one caveat I should point out here is that we still have to deal in this retrieval process with this transmissivity factor here, okay, which is a function of the density of the upper part of the ice sheet, which is not something that's well known a priori. So in our retrieval, we've demonstrated here at the moment, we have to look at the measurements near the boreholes where we know the true temperature. We look at the measurements near the boreholes and use that to infer something about these density parameters, that we then extrapolate those density parameter information to other parts of the ice sheet. So that means that our retrievals of temperature profiles aren't entirely independent of the borehole truth temperatures. We wish they were, but because of this nuisance parameter of the density that's not well known, we had to use that information to constrain those parameters. Nevertheless, once we did that, we can still retrieve the temperature as a function of position along our flight path. And we hope in the future to be able to eliminate that requirement by using other radar measurements and so on that would be responsive to those density type profile information. Here's an example of the kind of retrievals. Again, we're retrieving that surface temperature, things like surface temperature, geothermal heat flux at the base of the ice sheet, accumulation rate. These are parameters that go into our model for what the temperature profile is. Again, we have some ancillary information about what the surface temperature is like, for example, that's used as part of a Bayesian type retrieval process, but definitely the brightness temperature measurements get a lot of weight in correcting that to try and produce our final retrieved temperature profiles. And so this is an example showing how those parameters get corrected from the ancillary PDFs that are fed in to the Bayesian retrieval process. And here's the final temperature profiles that result from our retrievals. Okay, so this is along our flight line, which goes between the Camp Century, Neem, and In-Grip boreholes. And we're plotting here the retrieved temperatures in Kelvin as a function of depth in the ice sheet. Okay, and we see this general trend of warmer temperatures near the base, colder temperatures near the top, but we also see fairly significant variations along the ice sheet and with the ice thickness that our radiometric retrieval enables to retrieve these. Since we use a Bayesian retrieval process, we also get some information about the uncertainty of those retrievals, which is shown here. Okay, so this uncertainty is in the 0 to 3 Kelvin range, and it does increase as we go to deeper depths because of our the way the retrieval works. But overall, we do get new information from these retrievals that we wouldn't have had otherwise, and this is doing it by remote sensing methods. Okay. For sea ice thickness sensing, again, as I mentioned previously, we did a flight over north of Greenland over sea ice. We got some sea ice thickness retrievals shown here in this dash curve. This is the thickness versus position along our flight line over very heterogeneous ice cover. Unfortunately, here we didn't have ground truth to compare with other than some large scale things that show we were sort of reasonable in our retrieval. We didn't have precise ground truth to intercompare with. We deployed an instrument in the Mosaic Sea Ice campaign where we put our instrument out onto a sea ice flow that had a lot of good ground truth. And we've written a paper about that, showing that the forward modeling predictions match up with the measurements there using the in situ data. So we're getting ready to submit that paper and hope to see it out soon. So we've seen some progress in the area of sea ice thickness sensing that are kind of validating this concept of the utility of these lower frequencies. We've been doing some retrieval simulations just from a modeling point of view about, how much does having these lower frequencies help you? This is a plot here of the simulated errors from a simulation in this case, okay? If the true sea ice thickness is in the range 0 to 2 meters and the salinity of the ice is in the range 1 to 8 parts per thousand, then this plot here is showing the error you would get in your retrieval of thickness if you were to use only existing methods, the 1.4 gigahertz only. And actually, we think from these wide range of frequencies, you can retrieve not only thickness, but also salinity of the ice, which again is something that's never been retrieved before, which I think is an interesting parameter. If you only use 1.4 gigahertz, again, we can do pretty well for thinner ice, especially in the lower loss case. But as the ice gets thicker, we don't do so well. Whereas if we add our lower frequencies, we can extend that ability to sense thickness to a much greater range and also extend our performance over a wider range of salinities within the ice. So again, we think this extended frequency range will be useful for sea ice thickness sensing. So our third campaign was in Antarctica. This is through cooperation with our Italian partners. And you can see we were based out of Mario Zucchelli Station here. We flew to the Dome C station. We took measurements over the inland part of the ice sheet. We also took a lot of flights over the coastal sea ice in this region and so on. So we got ice sheet measurements as well as sea ice and ice shelves as well. So we're in the process of analyzing this data set. There's a lot of interesting things in there. We're hoping to be able to report. We have one paper that's been accepted about our measurements along this part of the ice sheet, and we're in preparation for one about our coastal measurements. Again, trying to demonstrate the additional information you get from these lower frequencies. Okay, so now I wanted to talk about a few, those are some evidence for this technology. I wanted to talk about a few of the challenges if we think about, well, could we ever do this in space? Okay, so what kind of challenges will there be? Well, one is the large aperture size, right? Especially 1.4 gigahertz, the SMAP antenna is like 6 meters. If we wanted to go even down to 500 megahertz and keep the same spatial resolution, we'd have to have an even bigger antenna. Okay, so we need a large antenna to make this work, something like in the range 10 meters or so, or we could push it down to smaller sizes, but 10 to 12 meters would be nice. But fortunately, those kind of technologies have developed a lot over recent years, and they're available, and they can be done with moderate swap requirements and so on. Large deployable reflectors are there. And actually, our European partners have made proposals for space missions using those kind of technologies already that are currently under review. So the development of technologies in this area really seems to make this idea more feasible for use in space. As we mentioned, RFI is a significant concern because that part of the spectrum is heavily used. But the advancement of the RFI detection and filtering technologies really motivates us here, as well as the fact that, in this part of the spectrum, 500 to 1400, there are significant parts that are reserved for things like radar operations or broadcast operations. And those systems are kind of designed inherently to not use the entire time frequency space. For example, a radar only transmits at a low duty cycle. So that leaves a significant portion of time available for doing thermal noise measurements if you can filter out those radar pulses. Broadcast applications are separating transmissions in space so they don't interfere with each other. So again, at a given location, parts of the spectrum are left unused. And so again, that gives us the idea that we think we can do these kind of measurements, especially if we're focused on things like cryospheric type science, where there's less spectral occupancy in general. And we compiled some occupancy statistics from our airborne campaigns that kind of give us some reasonable confidence. Now, we don't expect to have access to the spectrum 100% of the time, but again, even if we could have access to it only some fraction of the time, we can still have a good time bandwidth product to get a good radiometric resolution here, we think. We also need wide bandwidth receivers, and there are some challenges there. Typically, radiometer receivers are very narrow band because you don't want to have to deal with mismatch effects in the receiver and so on, which complicates calibration. But there's been a lot of innovations in these areas recently in terms of different designs. The UWB-RAD design uses so-called pseudo-correlation front end to help address some of these challenges. And also component performance over wide bandwidths continues to get better and better. So we think this is definitely addressable. Another concern, if we go into space, when we try to observe Earth's surface emissions from space, we have to go through the ionosphere. And the ionosphere impact does increase with frequency. As you go to lower frequencies, you get more impact. So we do need to address ionospheric impacts. Also, celestial sources and so on reflecting off of Earth's surface can be a significant contribution. Some of those are larger at lower frequencies than at higher frequencies. So we need to address those. But again, the success of addressing these for SMAP, SMOS, Aquarius, and the fact that these are reasonably well-known phenomena give us confidence that we think these could be addressed and still be able to produce good thermal noise measurements. Another option is if you observe at nadir and in circular polarization, you can reduce some of the ionospheric impacts as well. Okay, so based on all this, we think important areas to continue research in are looking at spectrum occupancy, trying to understand that better, both from measurements and from looking at licensing and so on, trying to continue to develop wideband antenna and receiver systems, so we can understand how to best build a receiver for this kind of thing, continuing to improve our RFI detection and filtering technologies, continuing to develop our models for predicting the brightness temperatures of these kind of materials in this frequency range, and also studying how to do retrievals. How should we do our retrievals to get back to our science products? Continuing to do ground-based and airborne demonstrations over a wider range than we've demonstrated so far, and thinking about more collaboration with scientists to think about the impacts of the new geophysical products that could be achieved from these kinds of measurements. Okay, so to wrap things up here, we're encouraged. We're very excited about the initial results we've seen and the ongoing progress in the development of this 500 to 14 megahertz radiometry. There's a growing community internationally looking into this and trying to explore it. So we do think continued development makes sense here, with the goal of eventually reaching progress toward the spaceborne system to produce science products that will be of value for the research community. Okay, that's it, and I'll stop there and be happy to take any questions.
Thank you, Dr. Johnson. So if anyone has any questions, they can raise their virtual hand, which is you can access by opening the attendee panel. There's a little hand icon. So if you raise your hand, I will unmute you. Or you can also ask your questions in the chats and I will read them out loud. Oh, here's our first question. Do you expect RFI to change by a lot and affect the current filtering due to the wide application of 5G networks?
Certainly, spectrum occupancy is a challenge for the technology I'm talking about here. It definitely continues to evolve and advance. I would say the 5G systems that are coming online are not really oriented towards this part of the spectrum. So those would be a little less of the concern compared to other parts of the spectrum, for example, 23 gigahertz, where a lot of radiometry happens, where we've seen, a lot of concern about interference there. Definitely the kind of this technology kind of lies in the realm of spectrum coexistence between our interest, which is as a passive user of the spectrum, and active users of the spectrum. The kind of technologies we're talking about here are so-called unilateral detection and filtering technologies, where the radiometer would try to manage the coexistence on its own with other active users. There are a lot of discussions and vision of the future in which we have bilateral coexistence in some frequency range in the future, where the active and passive systems would cooperate to share the spectrum. At the moment, that hasn't, that's still just a vision. So we have seen that these unilateral technologies, as we're talking about here, definitely you have to give something up because you lose sensitivity by discarding parts of time, frequency, space that are occupied by other users. But the fact that we've shown that you can still continue to make radiometric measurements that can produce science observations is what motivates us here to continue pursuing this.
Thank you. This next question is from Senya Gradsky. They ask, any proof of concept ocean salinity measurements in cold water?
That's a good point. I didn't talk about that here. Our instrument has done some over ocean measurements, but our group in particular is focused on the cryosphere, the sea ice and ice sheet products, so we haven't examined those extensively. I would say that our instrument measurements, the salinity product is one that requires very high precision, and our airborne instrument was designed to be precise, but not to that level of precision. So I'm not sure that we'll be able to demonstrate those from our measurement. We do have some collaborators in our team at JPL who have been working on doing some ground-based measurements to demonstrate the sensitivity to salinity. So that is one where we'd like to see some, we're very interested in seeing new evidence demonstrating those kind of products.
Okay, thank you. Does anyone have any other questions? Those are the two that I got initially. Oh, I just got one. I'll just read their whole message. They say, hi, Joe. This is Ziwu from NOAA. This is a great talk, very informative. Thanks. I heard recently that a group is proposing a NASA EVM mission using P-band to measure root zone soil moisture and snow water equivalent, SWE. I'm wondering if your team or any of the SMAP team members are part of that effort.
Well, I probably shouldn't comment about ongoing competition related things, but I can say there's a lot of interest in this part of the spectral range for not only microwave radiometry, like I've been talking about, measuring the thermal noise from the Earth, but there's also interest in using these frequency range for radar systems, as in the biomass mission or the SMOS EVS mission that has shown, sensing root zone soil moisture from radar backscatter measurements, as well as reflectometry measurements. Where, sort of like, as we know, the Cygnus mission of NASA measures specular reflections off of Earth's surface at 1.5 gigahertz. And there's a current CubeSat in development called Snoopy that will be doing similar kinds of measurements in this part of the spectrum, 400 megahertz and around that range, to demonstrate measurements of soil moisture at greater depths. So I think when you hear the term P-band, we need to distinguish between the radiometer type technologies like I've been talking about, the backscatter radar type technologies like biomass or SMOS, and the reflectometry type technologies like Snoopy, all of which are very interesting. They're all complementary. They all try to exploit this greater penetration to different degrees. For example, for the ice sheet temperature product, the fact that radiometry is inherently sensitive to physical temperature is what makes that product possible. That product wouldn't be possible with a backscatter measurement or a reflectometry measurement. So they all have different sort of areas in which they would have greater strengths or greater or lesser applicability.
Thank you. This next question is from Ming Li. They ask, the penetration depth is about 30 centimeters at 0.5 gigahertz. How do you get the simulation brightness at depth deeper than the penetration depth? You have obtained the simulation brightness at depth of 2,000 meters.
Yeah, I think we need to distinguish there between what kind of material we're talking about penetrating into. So, if we're talking about soils, and that's largely a function of the liquid water content of the material. So in like land surface, soil type surfaces, definitely the penetration into the material depends heavily on its water content, the soil moisture. On the other hand, when we talk about ice sheets, the liquid water is pretty much frozen. And especially in very dry, cold ice, the penetration depth of these frequencies can extend up into the kilometers range. And so those cases where I was looking at much greater depths, we're talking about very cold, dry ice, like you'd have in the middle of Greenland or Antarctica and so on. So I think that's probably relates to what was being asked there.
Okay, thank you. Another question. Does the sea salinity have diurnal variability so that you have to measure it in different diurnal times? I might be saying that word wrong.
So we're talking about sea surface salinity. The products that exist out there, for example, from Aquarius, SMAP, SMOS, they tend to be reported on a weekly or even monthly basis, because it takes very precise measurements to be able, the brightness temperature is sensitive to salinity, but the sensitivity isn't huge. And so we need a lot of averaging to get precise salinity measurements. And so those products tend to be reported as weekly or monthly products. And so it's not trying to measure any diurnal sort of effect. And I couldn't tell you whether I would expect there to be one or not.
Thank you. Any other questions? Anybody want to raise their hands too? And give another minute or so. Okay, sounds like that is a no. Well, thank you, Dr. Johnson, for giving us this great talk. And for everyone else, just remember to come in next week as our seminar series continues. Thanks everyone for showing up.
Thank you. Nice talking with you.
Thanks, Dr. Johnson. It's a great talk. We will send you the video recording once it's available. Thank you.
Great. Look forward to that. Thank you.
Have a great day, everybody.
Bye-bye.